Section 10.3, changes in temperature and phase. The three objectives here are to understand and apply specific heat capacity, to interpret a heating curve, and to calculate the heat needed for a substance to change phase and temperature. So specific heat is the amount of heat needed to change 1 kilogram of a substance by 1 degrees Celsius. And this specific heat capacity depends on the phase of the substance. For example, if we're looking at H2O, or we know as water, it has a different C value, whether it is a ice form, liquid form as water, or in steam form or the gas form. Now this value is given as the capital letter C, standing for specific heat capacity. So the formula we have here is Q equals mc delta T. And what this tells us is that the heat needed, Q, or the energy needed, is equal to the mass of the object or substance times its specific heat capacity times the temperature change in that substance. Again, this is not changing phase here. This is within a phase. So let's say for water, if you're going from 20 degrees Celsius to 80, delta T would be just final minus initial, so 80 minus 20, or 60 degrees Celsius. Let's take a look at our units to figure out what the units of C should be. So we know that joules are units for Q, mass is kilograms, leave C unknown, and our temperature change is degrees Celsius. So if I want to get joules equal joules, I need a joules up top, and I need to get rid of these kilogram degrees Celsius. This becomes kilogram degrees Celsius. And we'll see, cancel, 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 and we have joules equal joules. So the units of C are joules per the product of kilogram degrees Celsius. So here we have a table of specific heat capacities, and what we'll notice is that most of these are not really given as far as whether they're solid, liquid, or gas, but we do know that these are the three phases of H2O. We also, I think, know that by now mercury is a liquid at room temperature, so I'm guessing that's the liquid phase of mercury, whereas all the others are most likely solids, because we're looking at room temperature here. And what we'll see here right away is that, again, H2O has different C values for each of these different phases. The C value of the H2O, though, is higher than the other materials or other substances, which means that it takes more heat to change the temperature of a given quantity of, for example, ice, than it does for a given quantity of something like iron. So as the C value increases in a substance, or from one substance to another, the heat required also increases. And that's clear because Q and C are directly related. Q equals mc delta T. What happens if we happen to go too high in temperature with water that it becomes steam? It starts to boil, it starts to evaporate or vaporize. Well, then what we have here is what's called the latent heat. And latent meaning, dormant or within, the heat needed to change the molecular structure, really. The amount of heat needed to change the phase of a substance. And this is given by the capital letter L. In the last problem, we were given by the capital letter C for specific heat capacity. But this is the value we're going to use to see when phases are actually changing. So we call the heat of fusion the heat needed to change back and forth between a solid and a liquid. So this is either from ice to water or from water to ice, thus the biconditional. Or the heat of vaporization is when you want to boil water or condense gas into a liquid. So liquid to gas or gas back to liquid. And the formula given in this case is just Q equals ml. And you might ask, well, the last one was Q equals mc, but then there was delta T. Where's the delta T here? What you should realize is that there's no change in temperature when you're changing phases. Remember, think about water. Water, or ice in this case, ice is ice and it's below freezing or below 0 degrees until the molecules individually get up to 0 degrees Celsius. Then they start to change into water from ice. And it's not changing temperature, it's still 0 degrees Celsius, and then it starts to increase temperature once it's all become water. So during that phase change, there is no temperature change, theoretically. Now, realistically, there could be some, but we're going to assume that there's not. So we can look at these as little pieces of a function. So if something like water in the form of ice were to melt, it would go through a temperature change, then a phase change, and then another temperature change most likely afterward. So we're going to see little pieces of this. Now let's figure out the units of L. Since this is joules, and this is kilograms, it means that L must be joules per kilogram. And I know that because the kilograms need to cancel to give me joules equal joules. Now let's take a look at some examples of what we're talking about here. And what the table has done is it's used rows for each of these substances. So this, for example, is nitrogen. Let's look at water, because water is one that we know very commonly. So for water, and we can kind of break the table down like this. For water, we're going to see that the melting point, or you can call it the freezing point, meaning the phase change point either from solid to liquid or liquid back to solid, is 0 Celsius. The L value for the phase change or the heat of fusion is this quantity, 3.33 times 10 to the 5. Whereas the L value to go from a liquid to a gas or a gas back to a liquid is much higher, almost a full order of magnitude higher, 2.26 times 10 to the 6. And the boiling point or condensing point of H2O is 100 degrees Celsius. Now, the reason we need these values is because what if water went from something like, say, I don't know, negative 20 degrees Celsius to 50 degrees Celsius? Well, clearly it goes from negative 20, then it hits this phase change point where it becomes a solid to a liquid, then it goes from 0, that's at 0 degrees, then it goes from 0 all the way up to 50. So we have to look at this in little pieces, so we need to know where the melting and boiling points are for the substances that we're interested in using. Next, let's take a look at the heating curve for water so we understand what a heating curve is. And what this tells me is that if we consider this the baseline, right, the baseline of energy, we call this like the origin on the x-axis, this is x equals 0, the 0 line for energy. If ice at negative 25 degrees were heated up to then change phase, this would take 0.522 times 10 to the third joules of energy for this to occur. So the energy needed to go from negative 25 degrees to 0 degrees Celsius is again 0.522 times 10 to the third, which is just 522 joules. Now, the next part says this. If I want to then go from 0 degrees Celsius, now we're in like the ice-water phase, and I want it to start to change and change it all to water, right? So I want to change all of this ice to all of this water here at this point. Well, then at this point we have to say how much energy is needed to do that. Well, we take the 3.85 minus the 0.522. That's the change in energy level that is needed to change it from ice to water. And we take that number, remember, and multiply the answer times 10 to the third joules. Okay, that's the amount of energy needed to do that. But then suddenly we see the energy needed to go from 0 degrees Celsius in water to 100 degrees Celsius in water where it would start to turn to steam. Right, this change, right, 0 degrees Celsius to 100 degrees Celsius. The energy needed here would be 8.04 minus 3.85. You would subtract this high energy minus the lower energy amount. Then we're going to see this big jump in the graph right here because this is such a large change in Q. So it takes a lot of energy to vaporize water, a lot more energy than it does to make water go from a solid to a liquid or melt some sort of ice. So here we can see that 30.6 minus 8, we're looking at like a difference of 22 here, much greater than this difference earlier of only around like 5 or so. Okay? And then finally, to continue heating up steam, it takes a little bit more energy to continue that process. So B and D are phase changes. A, C, and E are temperature changes. So we'd have to use different Q values for each of these and different formulas for each of these and different C and L values for each of these as well. So this is really a good example of a piecewise function from math class. So example 1 says, determine how much energy is needed to change 500 grams of water at 50 degrees Celsius to steam at 130 degrees Celsius. So we know already that we're passing a phase change if we go from water to steam. And I'm not having to deal with heat of fusion because there's no ice in this problem at all. So I'm going from water to steam. So what really happens is it goes from 50 degrees Celsius, it absorbs some heat, it goes up to 100 degrees Celsius, it absorbs more heat to change phase, then it goes from 100 degrees Celsius to 130 degrees Celsius by absorbing more heat. So there's 3 stages here. Heat needed to change the temperature, heat needed to change the phase, heat needed again to change the temperature. Now, we could sum these together at the end of the problem to get a final value. I'm going to do these separately, but I want to also make note that we could write these all together. So I could write this as the following. I'm not going to do it this way, but I could write this as follows. Okay, I'm going to use that at the end, obviously, but I could replace this if I wanted to with mC1 delta T1 plus mL plus mc3 delta T3. I'm just using 3 because it's consistent with the subscript from above. I don't really need a 2 here. Okay, I don't need anything because there's only one L in this problem. The mass is the same throughout the whole problem, so I could factor the mass out and leave it out front. Alright, so I could do this problem this way. Now, I'm going to calculate Q1, Q2, and Q3 separately, and I'm doing it for a reason, so we can see what their relative values are. But really, you could calculate it with this big, long formula at the end. But let's calculate it all separately. So again, mc delta T, the mass is 500 grams, or 0.5 kilograms. Now, C is the specific heat capacity in the water phase, because we started at 50 degrees Celsius, so it's currently water. And water is 4.186 times 10 to the third. I'm going to write it as 4186, and this is from the first table in the video. Joules per kilogram degrees Celsius times the temperature change. Well, it's always final minus initial, and that's important. So 100 degrees Celsius minus 50 degrees Celsius. The reason that's important is because if we had gone down in temperature, technically speaking, we're giving off heat, so it's exothermic. So the Q value for that problem would be negative, showing that we're giving off heat, whereas Q here is going to be positive because the substance is absorbing heat. Okay, and then we'll get a value for Q1, whatever that is. Q2 is the heat that it takes to change phase from the water to the gas, and we use mL. So that's just the mass times the latent heat of vaporization, not the latent heat of fusion. Be careful. 2.26 times 10 to the 6 joules per kilogram. Okay, and that's going to equal some value we'll write down here. And then finally, the last part we have to take a look at is when the steam then goes from 100 degrees Celsius to 130. So it's again going to be M. Now this is a different C value. It's the specific heat capacity of steam, which is less than that of water from up here from earlier. So we can already predict that this number is going to be smaller than the value we're going to get for Q1. Times 130 degrees Celsius minus 100 degrees Celsius. And that's clear that the delta T is also less, right? This is a change of 50, change of 30. This is a big number, this is a smaller number. So this number has got to be bigger than this answer we're going to get. But we're hoping, or we're going to see probably this is going to be the biggest of all, because this is involving a phase change. So again, we're looking for what Q3 is at the end here. So let's figure out what these numbers are. The first one turns out to be 104,650 joules. The second one is 1,130,000 joules. And the third one is only 30,150 joules. So we go back up to our original formula, which told us that the total Q is equal to the sum of the Q's. So we add those values together. Okay, we can write it this way, or just simply write it as Q1 plus Q2 plus Q3. Remember that this simply means the sum of all the Q's from Q1 to Q3. All right, adding those three up, we get 1.26 times 10 to the 6th joules. So it's a positive answer again because it absorbed energy. Had it been a phase change or lost temperature, it'd be giving off energy, thus it'd be a negative answer. Let's talk last about one thing called calorimetry. Okay, and calorimetry is the idea that if a substance gives off heat, it has to be absorbed by something else. So imagine that we had an unknown substance and we had a bath of water. Okay, so this is filled with water. And we take this unknown substance with a given mass, we know what the mass is, and we drop it in the water. If we can determine how much heat is given off by this substance, we can then define its specific heat capacity. And think about this for a second. If this is a controlled system where no heat is escaping, it's fully insulated, imagine. Okay? The heat that the object is or has will be lost into the cold water. So the water will absorb it. So in essence, the heat given off by the unknown substance equals the heat absorbed by the water. And this is conservation of energy. But we know that the heat given off by this substance is the mass of the substance times its specific heat capacity, which is what we're looking for, times the change in the temperature of the unknown substance. The mass is measured with a scale. The change in temperature of this can be measured with a thermocouple or a thermometer. Finally, if we look at the water component now, we can know the mass of the water that can be measured, we know the specific heat capacity of water, and we can measure the change in temperature of the water. So the only unknown would be the specific heat capacity of the unknown substance. So this was a way that was used to determine specific heat capacity of unknown substances. For a long time, calories in food were measured using this process by putting the substance in water and completely burning it, actually, and determining how much heat was released by looking at the change in temperature of the water. We know the mass of the water, we know the mass of the object, we can measure this, we can measure this, we know the specific heat capacity of water, so we could find the specific heat capacity of the substance. And that's how calories were measured for food for a long time. Again, remember that this is all due to conservation of energy, and this is called calorimetry.